Math 1314, Tyler Junior College, Section 3.2, Polynomial Functions. In the previous series of videos for Section 3.1, we studied quadratic functions and pretty much everything we could figure out about them en route to sketching a graph. What was the vertex? Did the graph open up or down? What was the y-intercept? What were the x-intercepts, if there were any? And we followed through by discussing the maximum and minimum value of a quadratic function based on whether its parabola opened up, in which case the vertex represented a minimum, or the parabola opened down, in which case the vertex represented a maximum. And we looked at some applications. But quadratic functions are limited because by definition the highest power they can contain is a second power. Quadratic means degree of 2. We could try to do the same thing we did before by raising the degree to 3 and just discuss a thorough discussion about cubic functions. And all of that would be pretty interesting. Where do we stop raising the power? I mean, after we start talking about third degree polynomial functions, do we then talk about fourth or fifth or sixth, and where do we stop? Well, the answer is once we go past quadratic functions, polynomial functions, whose highest power is x squared, then we start talking about them a little bit more generally as just polynomial functions, regardless of what the highest power is. In order to do this, we need to first define what we actually mean by a polynomial function. I've kind of got the definition started, but I wanted you to watch me fill in the rest of it. A polynomial function is a function equivalent to the following form. I'll explain what equivalent means later. But for now, let's write what most of them look like. Most polynomials start with the power of x. But to represent that power generically, we'll just say x to the nth power. Now, there is a coefficient, a number multiplied in front of the x to the nth power. If you don't see it, it's because it's the number 1, but we need to represent it generically. So let's just represent that first coefficient with an a. Now, if our polynomial is written in general form, then it will start with the highest power and progressively go down in power. So for the next power, we need to represent 1 less than the current power, so that would be x to the n minus 1. But now the problem is, what do we call the coefficient? We could call it b, like in the quadratic functions, we had ax squared plus bx plus c. But the problem with putting b here is that we don't know how many terms we're representing because it's generic. It's theoretically possible that we could run out of different letters to represent the coefficients. If our polynomial was, say, degree 30, in which case we would actually have 31 terms, and we would run out of letters to represent the coefficients. So we need something a little bit more resourceful to label the coefficients instead of just running through the alphabet. A standard technique to recycle a variable is to use it over and over again, but subscript it with something. So we're going to generically represent the coefficients with a's, but we need to subscript them to indicate that they belong to the certain power of x. And in order to indicate that, we're going to subscript a variable with a number that matches the power. So we're going to subscript this first a with an n, and you could read that a sub n, meaning I'm the coefficient of x to the nth power. Following suit, we would label the next coefficient a sub n minus 1. Now don't let the notation throw you off. This is simply saying I'm a number in front of a power of x. That's all it's saying. And this continues. How long? Well, until we run out of x's. So although a polynomial function written in general form can start with any power at once, I know where it's going to end. Eventually, I'm going to get down to x squared. So I can write its coefficient as a2, and then x to the first, or just x. So I can write its coefficient as a1, meaning the coefficient of x to the first power. Got that a little bit better. And at the end, we run out of x's, so what should I call it? Well, it's the constant term, but it's technically a coefficient, even though it's not in front of an x. So if we were to name it the same thing as we did these, it would be an a, subscripted with the power of the x on it, where there are no x's, which is why we're going to call the constant term a0. And I have to state what all these things represent. So, a polynomial function is a function equivalent to this form, a bunch of powers of x's with numbers in front of them, where lowercase n is a whole number, which means it can't be a fraction, can't be a decimal, well, unless that fraction or a decimal is a whole number, but it can't be a negative number. Whole numbers start with 0, 0, 1, 2, 3, 4, etc. And each coefficient, we're going to generically call it AI, because we don't know which one we're talking about, so we'll subscript that with something generic, where each coefficient AI is a real number. So the coefficients can be pretty much anything, as long as it doesn't have an I in it, which is funny because I used I as the subscript there. Maybe I should use something else. Let's just call it AK. It really doesn't matter what I use as the generic subscript. I'm just saying all the A's are real, all the coefficients are real. So no imaginary numbers. But real numbers include things like decimals, fractions, irrational numbers like pi or the square root of 2. A little bit more terminology before we answer the following question. When you have a polynomial function, there will be a term with the highest power. The term with the highest power is called the leading term. Now be careful. What makes it the leading term is not the fact that it's written first, because it doesn't have to be. This is just a general form. What makes it a leading term is it is the term that contains the highest power. The coefficient of the leading term, so the AN, is called the leading coefficient. And again, what makes it the leading coefficient isn't the fact that it's first. It's the fact that it's the coefficient in front of the x with the highest power. Speaking of the highest power, n, is called the degree. And I've used that word quite a bit, but now I'm officially defining it as the power on the term with the highest power in a polynomial function. So let's take a look at the following 4 functions and decide which are polynomial functions. Remember, the exponents have to be whole numbers. Well, the first one has to be a whole number, but by subtracting 1 from it, it's going to stay a whole number as long as we don't go negative. And the coefficients have to be real. No i's in the coefficients. So let's take a look at the first function. F of x equals negative 3x to the 5th plus the square root of 2 times x squared plus 5. Does it satisfy the criteria for being a polynomial function? Is the degree a whole number? Yes. And more specifically, are all the powers whole numbers? Yes, 5 and 2 are whole numbers. Are the coefficients real numbers? Negative 3 is real, it's on the number line. So is the square root of 2, and so is 5. So it satisfies all the criteria for being a polynomial function. So yes, it's a polynomial function. But what about b? G of x equals negative 3 square root of x minus pi times x to the 3rd power minus 17 halves times x. Well, all the coefficients are real. The coefficient here is negative 3. This one's negative pi. This one's negative 17 halves. All of those are on the number line, so they're real. But there's a problem, and it's with the first term. Nowhere in the definition of a polynomial does it say that a square root is allowed, but we can be a little bit more rigorous than that. Because in previous videos, we've talked about the relationship between radicals and rational exponents. Specifically, that if you have a radical whose index is n with the square root, the implied index is 2, and underneath has an exponent of m, the implied exponent here is 1, then you can rewrite this as x to the m over n power. Excuse me, to the m over n power. So specifically for the square root of x, that's the same as the second root of x to the 1st power, which is equal to x to the 1/2 power. That's a problem, because in a polynomial function, the exponents have to be whole numbers. So no, negative 3 times x to the 1/2 power is not a whole number power. What about C? H of x equals negative 3 over x squared plus x to the fourth plus 19.2. It should be pretty transparent. The only issue maybe is the negative 3 over x squared. Because even though 2 is a whole number, that x squared is in the bottom of a fraction, and nowhere in our definition of a polynomial function does it account for that. But I want a little bit better reason why. There's an exponent rule that I don't think we've discussed yet, so I'm just going to bring it out into the open. If you take anything, we'll call it x, and raise it to a negative power, we'll say negative n, then that is equal to 1 over x to the positive power. So for example, if we had negative 3 over x squared, because that's the issue, or that's the thing that could be an issue, we could rewrite that as negative 3 times 1 over x squared, and then according to this rule for negative exponents, we could rewrite this as negative 3x to the negative 2. For those of you heading forward to calculus, both of these exponent rules need to become second nature. So in this case, the answer is no, because negative 3 over x squared equals negative 3x to the negative 2, and that is not a whole number power. Negative 2 is an integer, but a whole number by definition is a positive or integer or 0. What about the last one? J of x equals negative 3x to the fourth times x minus 2 times x plus 3. This has things that our definition doesn't, namely parentheses. But notice that the definition says a polynomial function is a function equivalent to the form. So it doesn't just have to look like this. But we need to be able to, if we can manipulate it to look like that, then we're a polynomial function. I think you see how this is probably going to play out. Although this has parentheses and the definition says you're equivalent to something that doesn't, I can eliminate the parentheses by first foiling the two binomials. If I multiply x minus 2 times x plus 3, I'll get x squared plus x minus 6. Don't see it? Foil it. And then I can distribute the negative 3x to the fourth, which will give me negative 3x to the sixth minus 3x to the fifth plus 18x to the fourth. That's the correct form. The exponents are all whole numbers, coefficients are real numbers, so this one's yes. There is one more thing I wanted to do real quick on A and D since they were both yes. I just wanted to quickly identify the leading coefficient and the degree. The degree on the first one is the highest power, which would be 5. And the leading coefficient, which I will be abbreviating soon, capital LC, is just the coefficient in front of the x with the highest power, so the leading coefficient is negative 3. What are the degree and the coefficient for, what are the degree and leading coefficient for D, J of x? If you said the degree was 4, you looked a little too early. You can't really see the degree until the polynomial is written in general form, although there is a way to recover the degree when it's factored. But either way, the degree is 6, and the leading coefficient is negative 3. So we're only going to be studying polynomial functions in this section. Just remember, exponents are whole numbers, and no i's anywhere.